All right, so we are going to talk about some extraneous solutions. So let's start by looking at this warm-up. Take a moment, pause the video, and answer the questions. All right, so when we are checking if an x value is a solution for a given equation, we take that x value and we plug it in for x. So if I replace x with 2 in my equation, the left side simplifies to be 6 minus 1, which is equal to 5. That does not equal 4, so x equals 2 is not a solution to this equation. So an x value is a solution when it satisfies the equation. So when you plug it in everywhere that there is an x and simplify on the left, simplify on the right, the left side should equal the right side. Here is another warm-up, so take a second, pause the video, and check your solving skills. All right, our solutions are 23 and 64. For the first one, we can get that by cross multiplying. 2 distributes in to 2x minus 4, and 3 distributes in to x plus 5. When we distribute, we get 4x minus 8 equals 3x plus 15. We need to get our x's on one side and our not x's on the other. 4x minus 3x is just 1x, and 15 plus 8 is 23. For the second equation, we have a square root function. So we need to isolate the square root function, or the square root, and then undo that square root. So first, we get rid of the 1, and so we have 1/2 square root equals 4. If we multiply both sides by 2, we end up with the square root all by itself. So then when I square both sides, 8 squared is 64, and there's our solution to this warm-up. All right, so our goal is to go a step further than just solving and build an understanding of what an extraneous solution is and how to recognize when we've found an extraneous solution. One thing I like to focus on when looking at the word extraneous is the word extra. It's this extra unnecessary solution. So anytime you're trying to spell the word extraneous, I kind of think of it as extra neo-us. Just like sometimes you think Wednesday as Wednesday to make sure you spell it right. Extraneous is the word, but you can spell it out extra neo-us, so you can always spell that word. So extraneous solutions, we're going to look at this situation. We have Jasmine, Kevin, and Francisco working in a group, and they're asked to solve the equation 2 over x equals 2x minus 3. So take a second, pause the video, and try solving this equation on your own. All right, so now we're going to look through Jasmine, Kevin, and Francisco's methods to solving. Jasmine graphed 2 divided by x, that is this function, and the linear function 2x minus 3. There's our linear function 2x minus 3, a slope of 2 and a y-intercept of -3. Jasmine found the intersections between these two functions to be x equals 2 and x equals -1/2. That's a fully graphical method. Kevin's method was all algebraic. Kevin cross-multiplied and found a quadratic equation. He got that quadratic equation equal to 0 and then factored and set each factor equal to 0 to solve. Kevin also found those same two x values. Francisco kind of did a combination of the two, and instead of going to factoring to solve the quadratic equation, same one that Kevin found, Francisco graphed the quadratic and found the x-intercepts because that's where the value of the function is 0. And those x-intercepts are also at negative 0.5 and 2. The next equation the group was given to solve was 4x minus 2 equals the square root of x plus 3. So take a second, pause the video, and try solving this equation on your own. All right, so let's look at Jasmine, Kevin, and Francisco's work again. Again, Jasmine used all graphical methods, and Kevin stuck to algebra, and Francisco combined the two. So Jasmine's method takes our square root function and the linear function, and we find one intersection, one solution, one x value where the two functions are equal. Kevin's method gets two solutions, x equals 1/16 and x equals 1, the two solutions to a quadratic equation. Again, Francisco's method also finds the same quadratic equation and looks for x-intercepts, and they happen to be at 1/16 and at x equals 1. So both Kevin and Francisco's method resulted in more solutions, extra solutions, right? So we know that Kevin and Francisco have too many solutions because Jasmine's method shows the original equation only has one solution. So take a second, answer the question, what do you think causes the extra solutions? Why do you think extra solutions happen? All right, so let's get into some notes. Make sure you have somewhere in your notebooks or binders these notes written down so that you can use them on your exit ticket first thing tomorrow. An extraneous solution is a solution to an equation that emerges from the process of solving the problem, but is not a valid solution to the original problem, the original equation. If I plug that back into the original equation, it will not make it true. Just like an incorrect answer from work with mistakes in it would, these answers come from all correct algebra and still don't work. So when you check for extraneous solutions, solve the equation like normal. Then always at the end of your solving process, you will substitute in the values you got from solving to check for extraneous solutions. If you get a true statement, the left side equals the right side, then you have a valid solution. If you get a false statement, the left side does not equal the right side, then you've either made a mistake in your algebra or you have found an extraneous solution. Both scenarios cause this false statement, so be very careful and make sure you check your algebra and are very confident in your answer, and then decide if it's an extraneous solution or not. Only list valid solutions in your answer. So if you get x equals 2 and x equals 3/2 for two solutions, and you find that 3/2 is extraneous, I like to put a box around the valid answer and say extraneous, extra, neo, us, next to the extraneous answers. So you show me, hey, I knew how to do the algebra. I knew how to find all the possible answers algebraically, and I know that this one isn't valid. This one is. Okay? So leave that in your work. Don't erase it. I want to see that you knew how to find it and that you recognized it is not a valid answer to the solution. So let's check some examples. The square root function is the most likely place you'll see extraneous solutions. It's possible that for our inverse variation or reciprocal function to result in extraneous solutions, but it is much more rare because extraneous solutions happen due to domain restrictions. So when I solve this equation like normal, I'm isolating my square root. I get the square root expression by itself, and then I square both sides to get rid of my square root, to undo that square root. -3 times -3 is +9, and the square undoes the square root, so I just keep what was under the square root. Now I can isolate x, add 5 to both sides. I have 14 equals 2x, and therefore x must equal 7. To check if 7 is a valid solution or not, I'm going to plug in 7 to the left-hand side, but there's no x in the left-hand side. So the left-hand side is always 7. The right-hand side is 10 plus the square root of 2 times x. I'll replace x with 7, minus 5 all under the square root. Let's simplify this. We're going to simplify under the square root first. That's 14 minus 5 under the square root. So we are adding 10 to the square root of 9. That's 10 plus 3. That's 13. 13 does not equal 7. So we have an extraneous solution. (14 minus 5 is 9. 10 plus 3 is 13. 7 does not equal 13. So this is an extraneous solution, and I don't box extraneous solutions. This equation has no solutions. All right. Now let's get into the next example. If you feel confident in the process, take a moment, pause, try it on your own. Our square root is already isolated, so I will square both sides to isolate 3x plus 1, and then I will square x plus 1. Now remember, x plus 1 squared is x plus 1 times x plus 1. Don't make this x squared plus 1 squared. That's not the case. You have to multiply binomial times binomial and FOIL. First times first, outers, first outer, inner last, FOIL. So the first x times x is x squared. Outer is x times 1, that's x. Inners are 1 times x, that's x. And last, 1 times 1 is 1. So we have 3x plus 1 equals x squared plus 2x plus 1. Recognize that you have a squared term and a not squared term. That is a quadratic equation. So we're going to get our quadratic equal to 0. Move every term over to one side. And 1 minus 1 is 0, so now I have an A term, a B term, and no C term, which means I can solve this by factoring just to GCF. So if I factor out x, I have x minus 1 left. I can set each of those factors equal to 0. The first one results in x equals 0, and the second one results in x equals 1. So I have two solutions to check. The first one I'll check is x equals 0. So the left-hand side, when x equals 0, is the square root of 3 times 0 plus 1. That is the square root of 0 plus 1, or the square root of 1. 1 times 1 is 1, so the square root of 1 is just 1. The right-hand side, if I plug in 0 plus 1, that's 1. Since 1 equals 1, x equals 1 is valid. Now remember, sometimes it's tempting to plug it into the squared version, but remember, our original equation is what we're going back to. We are not including what we did to that equation. And the reason that is because our square root has a smaller domain than our quadratic function. we only accept x values that won't make this square root negative, right? But this quadratic function is going to allow any x values. The domain of quadratics are all real numbers. So there may be an x value that will satisfy this equation that does not work in the domain of our square root function. So let's see if our second solution causes that issue. X equals 1 if I plug in for the left-hand side. That is 3 times 1 plus 1. So that is the square root of 3 plus 1. Square root of 4 is 2. The right-hand side is 1 plus 1, positive 2. Since 2 equals 2, both of these solutions are valid. X equals 1 is valid. And I realized I wrote x equals 1, but this should be x equals 0, because that's what I was checking. I was checking x equals 0. I plugged in 0, so x equals 0 is valid. I was checking x equals 1. I plugged in 1, so x equals 1 is valid. All right, so 0 and 1 both work. Now let's look at a reciprocal function. Take a second, pause, and try and solve it on your own. First things first, I will isolate the fraction. So I have x plus 2 equals 8 divided by x, and I think of x plus 2 as x plus 2 over 1. So I can cross multiply 8 times 1 equals x plus 2 times x. I distribute x into x plus 2. So this is 8 equals x squared plus 2x. I see an x squared and an x, so that's quadratic. I need to move this 8 over, minus 8. And now I'm factoring. I want two numbers that multiply to negative 8 and add to positive 2. 2 and 4, where the 2 is negative, should do the trick. So I have x minus 2 times x plus 4. I'll set each of those factors equal to 0 in order to find our solutions. X minus 2 equals 0 gives me x equals 2, and x plus 4 equal to 0 gives me x equals negative 4. If I plug those solutions back in, check the left-hand side. If I'm checking x equals 2, the left-hand side is 2. The right-hand side is 8 divided by 2 minus 2, which is 4 minus 2, that's 2. Since the left-hand side equals the right-hand side, x equals 2 is valid. Now let's check x equals negative 4. The left-hand side is x, that is negative 4. The right-hand side is 8 divided by negative 4 minus 2. 8 divided by negative 4 is negative 2. Minus 2 is negative 4. Negative 4 equals negative 4, so x equals negative 4 is valid. So we have two valid solutions, 2 and negative 4. All right, now we have example number 4, another square root function. So I need to isolate my square root, add 15 to both sides. So I have 3 square root x plus 7 equals 3x plus 15. 3x and 15 are not like terms, so I can't combine them. Last, I divide 3, and I'm dividing the whole side by 3. So x plus 7 is all by itself now. 3x divided by 3. Remember, I can divide each of these terms by 3. So I have 3 divided by 3 is 1, that's 1x, and 15 divided by 3 is 5. Now I'll square both sides to get rid of my square root now that it's isolated. So I have x plus 7 equals x plus 5 times x plus 5. So that's x plus 7 equals x squared plus 10x plus 25. I'll get it equal to 0 so I can try and factor. So I subtract an x, that leaves me with 9x, and subtract 7, that leaves me with 18. So I need to multiply to 18 and add to 9. 3 and 6 should do the trick. So we have x plus 3 times x plus 6. I can set each factor equal to 0. X equals -3. X plus 6 gives me x equals -6. And now it's time to check, because we have a square root function that as we were solving, we started solving a quadratic function. The square root function has a smaller domain than the quadratic function, so we need to double check that these answers are in the domain of our square root function. So when we plug in, we're going to check x equals -3 first. We'll look at the left-hand side. -15 plus 3 times -3 plus 7 under the square root. We'll simplify this one. -3 plus 7 is +4. So I have -15 plus 3 times 2. That's -15 plus 6, which is -9. If I go to the right-hand side and I plug in x equals -3, I get 3 times -3, which is -9. -9 equals -9. So x equals -3 is valid, and I'll stick it in a box. Now I'll check x equals -6. The left-hand side is -15 plus 3 times the square root of -6 plus 7. That's 15 plus 3 times the square root of 1, which is just 1. So -15 plus 3 is -12. Now I'll check the right-hand side. If x is -6, and I plug in 3 times -6, I get -18. -12 does not equal -18. So x equals -6 is extraneous. Extraneous. And I don't put non-valid solutions in boxes. So x equals -3 is the only valid solution. Alrighty. Another inverse variation example. We're going to cross multiply when we have fraction equal to fraction. We have x times x plus 6 and 8 times x plus 3. Now, it's less common that inverse variation functions have extraneous solutions, but it's still possible because they do have domain issues. Our inverse variation function has a vertical asymptote at x equals 0, and if we shift our functions left and right, our asymptote moves left and right. So we have to make sure that our solution doesn't land on the x value of the asymptote from our solving. So just always make sure you are checking by plugging back in. So I have x times x is x squared, 6 times x is 6x, 8 times x is 8x, and 8 times 3 is 24. I have an x squared and an x, so I need to get all of it to one side. If I subtract 8x from both sides, I get 2x on the left, and subtract 24, don't have any like terms to combine. Now that it's equal to 0, I can find two things that multiply to -24 and add to -2. I'm thinking of 6 and 4 with the 6 negative. So x minus 6 times x plus 4 equals 0. X minus 6 equals 0. X plus 4 equals 0. X equals +6. X equals -4. If we check both of our solutions, if we check x equals 6, the left-hand side is 6 divided by 6 plus 3. That's 6 over 9. Which simplifies to 2/3. The right-hand side, 8 divided by 6 plus 6 equals 8 divided by 12. which simplifies to 2/3. Divide both by 4. 2/3 equals 2/3, so x equals 6 is valid, and I'll stick it in a box. Now we'll check x equals -4. The left-hand side is -4 over -4 plus 3. That's -4 over -1, which is +4. The right-hand side, 8 divided by -4 plus 6, is 8 divided by +2, which gives us +4, and those are the same, so x equals -4 is valid. Like I said, it's much more rare for reciprocal functions to have extraneous solutions, but it's totally possible, so always check. All right, that concludes our examples. Please find the homework worksheet on Canvas. I've also left the printouts with whoever's covering my class today, and you can take some time to go ahead and knock that homework out in class.